Okay, from page 883 and 884 in your textbook, you'll see an equation, this ln of k equals the negative delta H, R reaction divided by R, 1 over T, plus the delta S reaction divided by R. Okay, it's a really unusual formula. It's set up, if you realize that that equation is in slope-intercept form, so it's in y equals mx plus b form. If you pull the slope out of that equation, and you remember back to when you first learned what slope is, that is the change in y over the change in x, or the change in rise over the change in run, rearrange that so that delta y equals m delta x. Then bring those values down from the y equals mx plus b and substitute. And remember that delta means change, so that's x2 minus x1 and y2 minus y1. We can get this new equation that allows you to determine the k value, the new equilibrium constant, when you run a reaction at a second temperature. So if you are wanting to figure out what that equilibrium constant, that ratio between products and reactants will be, if you were to run the reaction at a lower, cooler temperature or a warmer, higher temperature, you can predict and calculate out that K value that you're going to see for that new reaction setting. So I worked here for you from page 891, question number 81. They give you the delta H of the reaction, negative 25,800 joules. The K value is 1400 for the equilibrium constant. The temperature is 298 Kelvin, standard thermo temperature. Now, what is K when we change the temperature to 655 Kelvin? So it looks like we pretty much double it and then some. Okay, so we set that equation, ln K2 minus ln of 1400 equals a negative with the negative 25,800 divided by the R value, and then 1 over 655 minus 1 over 298 for the temperatures. Okay, so we get all that set in there. And then we solve out and we get ln of K2 is equal to this 1.56 and several decimal places there. And then we can, on your calculator, do second function of ln, so you get the EX button of that 1.56 value there, and you'll get your new K, your new equilibrium constant, at about 4.8. Okay, at 4.8. So the K drops from 1400 to 4.8 when you increase that temperature by that much. So that actually keeps you from making the products. The products don't want high temperature, so the production of the final product is hindered by increased temperature. So if we want a greater K value, so we get a greater ratio of products to reactants, we need to lower the temperature from 298 rather than increase it.